So for today's discussion, we'll be doing two sections, section 3.5 and 3.6. So topics are vector fields, introduction to that, and curls and divergence of these vector fields. And also we'll talk about conservative vector fields. So I hope you've watched the lecture videos associated to these topics, the ones that were uploaded by the Institute of Mathematics in their YouTube account. Okay, so as usual, I'll be doing some problems. Okay, or I'll be showing you the solutions to the problems I have prepared. Some of them are typewritten, and then the others will do them during this discussion. Okay, so let us start with this problem. So we want to determine the curl and the divergence of this vector valued function, capital F, defined by y squared, comma 2y minus z, comma x, y, z. Okay. So in here, you may look at the definition of the curl of some vector valued functions or the divergence of a given vector valued functions. But in this solution, we'll be using our formula. Okay, so let's start with the divergence. So in here, the divergence of the function f, this is equal to del dot f. So we just recall that del operator, okay, this is what? This is quote unquote a vector, okay? A vector with components partial derivative with respect to x, comma, partial derivative with respect to y, comma, partial derivative with respect to z. Okay? And I'm writing the three components here because our f here has three components also. Okay? But if of course, if your vector valued functions is in Rn, then the components, quote unquote, of your del operator involves the first partial derivatives for each variable in your involved in your vector valued function. Okay, so this is an operator. Okay, this is an operator, and like I said, quote unquote, it looks like a vector. Okay, so with that notation, okay, we have to get the dot product, right? Del dot f. So it's just like this. We have the del. So this is that one. And then you get the dot product with this guy here. Okay. And this one operates like the usual dot product, usual dot product. But instead of, in the dot product, in the usual dot product, say you have x, y, z, you dot it with a, b, c. The answer to this is you multiply x times a. I'll just write this as ax, then plus you have by plus zz. So in here, you actually multiply component wise, and then you add the product. On the other hand, in here, you don't actually multiply it. You operate the partial derivative to the corresponding component of the vector valued function. Okay? So in here, we get this dot product here, and this will be equal to the partial derivative of y squared with respect to x plus the partial derivative of this guy here, 2y minus z, with respect to y, plus you have this partial derivative of this guy here, which is xyz, with respect to z. Okay? So it's not really multiplying. It's not really multiplying component-wise. What we do here is we operate the differential operator on the first factor here to the to the components, to the functions of the second factor here. And then you do component-wise, right? So if we evaluate this, of course, this one, partial derivative with respect to x, this is just y squared, it becomes 0. For this guy here, you have partial derivative with respect to y, and you have 2y minus z. So of course, derivative with respect to y of z, that will disappear. And then in here, partial derivative of xyz with respect to z, you treat xy as constant. So you'll have your xy here. And therefore, if we operate, we'll end up with 2 plus xy. So this is the divergence of this vector valued function. Okay? So that's the divergence. We now look at the curl. Okay? For curl, our formula would be cross product. Okay? And it's not your usual cross product because again, when you do your cross product, it must be a vector times a vector, okay? Vector cross vector, and when you do the cross product, there you are multiplying the components with some other components of the other factor. And then again, just like what we did in here, instead of actually multiplying it, we operate. Okay, we operate the differential operator involved from your del operator. Okay, but the way we do this, it's similar to the cross product. So we want to find curl of f. So this is del cross f, and this will be the del operator cross this function here. And as usual, if you can't remember the formula for the cross product, you can always use determinants of some 3x3 matrices, 3x3 matrix. First row involves your ijk. And of course, the second row, it contains the first factor in your cross product. And then your third row, it's your second factor in your cross product. So you want to get the determinant of this, okay? So if we try to do this, okay? If we try to completely calculate this, you will have something like, so equals quantity, you get this, okay? So it's partial with respect to y, partial with respect to y of x, y, z minus this guy here minus partial with respect to z of 2y minus z. And then this is multiplied to I hat. Then minus, you have something here, okay? You have something here minus, you have this guy and this guy, okay? Partial with respect to x. So partial with respect to x of x, y, z. Then minus, you have this and this guy here. Partial with respect to z of y squared. And then you have your j hat. And then you have times plus. Then we look at for the k hat. So you have this guy here, partial with respect to x of 2y minus z. Then minus, we have this guy here, okay, partial with respect to y of y squared. And then this is your k hat. Okay? So if we do the operation and we put it in vector form, I mean in this form, we will end up with this expression here. Okay? We will end up with this expression. So it's the vector x z plus 1, comma, then we have negative y z, comma, and then negative 2y. So this is the curl of our function f in here. Okay? Let me just remind you that for the curl, you will end up with a vector valued function. And then for your divergence, you will end up with a function in R2, R3, okay? So it's a function in the variables x, y, z in this case, since we are in R3. Okay? Questions? Okay. For our next problem here, so we want to determine the curl and the divergence of this function f of x, y, z equals ln of x, comma, ln of xy, comma, ln of x, y, z. Right? So, first, let us rewrite our function f of x, y, z here. So you have f of x, y, z. If you rewrite this, particularly these two components here, we'll just apply a loss of logarithms. Since you just have ln of xy, you can rewrite it as ln of x plus ln of y. And then you have ln of xyz, you can write that as ln of x plus ln of y plus ln of z. Okay? And from there, the solution will be a lot easier. So in here, you have ln of x, comma, ln of x plus ln of y, comma, ln of x plus ln of y plus ln of z. Okay? And then let's start with the curl. Let's start with the divergence. So we want the divergence of f. Okay? So this is again the del operator dot with your f. So this is equal to, let me just rewrite everything. We have here the partial derivative with respect to x, comma, partial derivative with respect to y, comma, partial derivative with respect to z, and dot it with this function, ln of x, comma, ln of x plus ln of y, comma, ln of x plus ln of y plus ln of z. Okay? And then in here, we'll just have, so I'll write everything. We have partial derivative with respect to x of ln of x. That's for the first component. I mean, that's coming from the first component. And then plus partial derivative with respect to y, coming from the second component. We have ln of x plus ln of y. Then finally, we want the partial derivative with respect to z of the third component, ln of x plus ln of y plus ln of z. And therefore, if we apply our operator here, or our operators here, we'll just have 1 over x plus 1 over y plus 1 over z. And that's the divergence of this function f. Okay. For the curl, so we want to find curl of f. So again, our formula would be the del operator cross with your function f. And then let's put the formula immediately. I mean the determinant. Okay. So we have the determinant I hat, j hat, k hat. And then in here you have partial with respect to x, partial with respect to y, partial with respect to z. And then down here we have ln of x, then ln of x plus ln of y. I think I will need a more space in here, so I'll adjust this. I'll also adjust it here, and then for the third and the last entry here, so partial with respect to z, we have here ln of x plus ln of y plus ln of z. And then we close that determinant. And then if we apply, this will be, again, I'll write everything. So for the first, I'll have these two guys in here. So partial with respect to y of ln of x plus ln of y plus ln of z minus, I'll have this, right? Partial with respect to z of ln of x plus ln of y. And then this is multiplied to I hat, then minus. For this, I have this guy and up to here. So we have partial with respect to x of ln of x plus ln of y plus ln of z. Then minus, I have this guy here. Partial with respect to z of ln of x. And this is multiplied to j hat. Plus, finally, we have this guy. So partial with respect to x of ln of x plus ln of y minus this guy here. Partial with respect to y of ln of x. Then this is multiplied to k hat. And therefore, in vector form, this is just what? So for the I part, we have this. This guy here does not have the z, so it's just 0. For this guy, I'll just have 1 over y. So that's 1 over y, comma. In here, I don't have the z again for this function, so that's just 0. So I'll have here partial with respect to x, and there's negative in here. So this is negative 1 over x, comma. This guy here does not have the y, and we are differentiating with respect to y, so that's 0. And then in here, that's just 1 over x. Okay, 1 over x. So I have 1 over x in here. And if all the calculations are correct, this will be the curl of our vector valued function f. Okay. Questions? Okay. Let us now go to our next problem. So for our next problem, we'll be talking about conservative vector fields, okay, and also potential functions. Okay? So the vector field F, this is conservative. So this function here, it is said to be conservative. So the problem is we want to find all potential functions of F. Okay? So what is this potential function? So you have a function, and if you get the partial derivatives, you add them, that should give you your capital F. Okay? So it says you have a function F. This is the potential. Okay? If F is the potential or is a potential, is a potential function of F, then what do we get? The gradient. Then the gradient of this F here, this is equal to capital F. Okay? And remember that the gradient of F, what is this? We have two variables in here, so let's just use two variables. This guy here, partial with respect to x of F, comma, partial with respect to y of F. Okay? Which means this guy here, if you have a potential function F, this guy here, it's equal to this part. And this guy here, it's equal to this part. Okay? So let's find all potential functions of F, since again, we know that it is conservative. So let f of xy be a potential function of F. Okay? Then the partial derivative of F with respect to x, it's equal to the first component of capital F, like I said earlier. And therefore, in here, we integrate with respect to x, treating y as constant. Okay? Treating y as constant. And therefore, if we integrate this with respect to x, treating y as constant, on the left-hand side, you just get f of xy. On the right-hand side, we integrate this, treating y as constant. We'll end up with xy cubed minus, in here, we integrate with respect to x. Again, treating y as constant, we'll have x squared y. And then ordinarily, if y were actually a constant, okay? For example, instead of you have y, say you have a function, let's say you have a value f of, or f prime, or let's use a different letter here or name. You integrate g with respect to x, you will end up with some capital G of x, and then you add the c. This is constant, a real constant. Okay? However, in here, since we are treating y as constant, this constant here is actually a function of y. That's why you have here g of y. Okay? So that's our first step. Actually, that's the second step. First step, you actually choose which one you want to integrate first. Is it the first component or the second component? Okay? So sometimes the one that is easier to integrate, that's to integrate first, that's the one you're going to use. Okay? So in here, we chose the variable, the first component. So you have this f sub x. we integrate with respect to x, we now have f of xy. So this is actually a potential. Okay, this is actually a potential. However, we have to identify this g of y, the actual form of g of y. It's a function of y. Okay, so in order to do that, what we can do, since we have used the first component, we have to use our second component here. And remember that the second component, it's the partial derivative of f with respect to y. So if we want to use this, we just differentiate this guy here with respect to y. So if we do that, differentiating with respect to y, we end up with this expression. F sub y of x comma y, it's equal to, so here differentiating with respect to y, treating x as constant, we'll have here 3xy squared minus in here you have x squared. And then of course, derivative of this with respect to y, it's g prime of y. And now this guy here, which is f sub y, should be equal to this expression. Okay? So using this guy, we replace this f sub y here by this. That is our left-hand side. Right? And then from the right-hand side, we have this. Okay? And then as you can see, if we simplify this, we end up with g prime of y equals to. So take note, your g, it's a function of y. Okay? And all constants, it can be a function of y. So whatever your variable is, the constant is a function of that variable. So these two here, it's a function of y. So this equation here makes sense. On the left-hand side, you have a function of y. On the right-hand side, you have a constant, which is treated as a function of y. Therefore, in order to find our g of y in here, since we have g prime of y equals 2, we'll just integrate. So that gives us g of y equals 2y plus this arbitrary constant c. So now this guy here, it's an actual arbitrary constant. So we have the g of y, okay, which is this guy here. And therefore, we now replace this here by this guy. And it gives us this expression. The potential will be of the form f of x comma y, it is equal to x y cubed minus x squared y plus 2y plus c. Okay, and this c here gives you that all possible potential functions for f or of f. Okay, so questions? Okay. So again, the solution, it's standard, right? It's standard. First component, second component. First component refers to the partial derivative with respect to the first variable. Second component, it's the partial derivative with respect to the second variable of the potential, right? So, like I said, you choose the component which is easier to integrate, right? And then once you've chosen that, okay, you do the integration, which you can do supposedly because it's easier to integrate, okay? And then to get the arbitrary constant in terms of the other variable, okay, you do the differentiation. So choose and then integrate and then differentiate. and then you compare the equations. After the differentiation, you compare it with the the um, the other component that you didn't choose. Okay, and then your remaining equation should make sense. If you have the function with respect to y, okay, then this part here, the function or the equation must give you a function with respect to y. Okay, if your function is with respect to x, okay, then the equation should give you a function with respect to x. Okay, and then you just solve for that missing function. Okay, so again, you can choose any component, first component or second component. You should end up with the same function. Okay. All right. Let's have another example here. So in here, you want to show that this vector field here is not conservative. Okay. So you want to show that this vector field here is not conservative. And we will do this by definition. Okay. Meaning, we will try to show that there is no potential function. Okay? Remember that by definition, your vector field is conservative if you can find a potential function. So in here, we will try to show that we cannot have a potential function, however we do it. Okay? So let's start. So assume F is conservative. So what we're going to do is to prove this by contradiction. So assume that F is conservative. It means if F is conservative, there's supposed to be a potential. So assuming F is conservative, let's take small f to be the potential of capital F. And then we do the process as in before. We choose either the first component or the second component. Okay, choose either the first component or the second component. And then once we chose which component we're going to use, of course, that should be the that should be equal to the partial derivative of f with respect to whatever variable. So in here, I chose the first component, which is 2xy. Since it's the first component, it must be equal to the partial derivative of small f with respect to x. Then, just like before, we integrate with respect to x, we treat y as constant. And since y is constant, after integrating, we will end up with a function on the right-hand side in terms of y only. That's your g of y. So we integrate 2x with respect to x, that's your x squared. You integrate y with respect to x, that's your xy. Plus this g of y. And then for the next step, we want to find our g of y. Take note, g of y, it's a function of y. So if we get the derivative with respect to y, so we want to get the derivative of this with respect to y, we will end up with x plus g prime of y. X plus g prime of y. And this is f sub y. And this is equal to the second component of your capital F. So again, your g of y here is a function of y, and therefore g prime of y must be a function of y. If we now replace f sub y by this 2x minus y, we'll end up with this equation. And then we solve g prime of y. We'll have this. g prime of y, it's equal to x minus y. And this is absurd because your g of y must be a function of y only. So if you get the derivative of that, it must be a function of y only. But in here, you have the variable x. Okay? And take note, we just use all the concepts that we know with the assumption f is conservative. If f is conservative, all the steps here are all true. Okay? All the steps here are all valid. But then again, we found a contradiction here, so something must be wrong. And in fact, that something is this assumption that f is conservative. So we conclude that f, this function f here, should not exist, and therefore your f, your capital F, is not conservative. Okay? Questions? Okay, understood. Okay, so let's do my last problem in here. Determine whether or not capital F given by this function here is conservative or not. If it is conservative, find all potential functions for F. Find all potential functions for F. Okay? We'll have a way in order to find a potential function, whether a vector valued function is conservative or not, okay, by using the definition. But you know, if your vector valued function involves or has three variables, if you are in R3, then an easier way to determine whether that vector valued function is conservative or not, okay, particularly it's easier to determine whether that vector valued function in R3 is not conservative by getting the curl of your function. Take note, that only works in R3 because remember, for your curl, our formula was to use the cross product, and cross product only works in R3. Okay? But in here, in this problem, our function, it's just in R2, or a vector valued function in R2. So for this, we'll do this by definition. Okay? So our solution is, well, we assume that it's conservative and we try to find all potential functions. If we cannot find that, then this is not conservative. Okay? So in here, we assume capital F is conservative. Okay? And let small f of x comma y be, let f be a potential function of f. Potential function of f, or for f. for F. Okay? So in here, like I said, you can choose any component, first component or second component. In my previous examples, okay, I started with the first component. So in here, I'll start with the second component, just to, show you that it also works. Okay. Then, so I'm starting with the second component. So I have f sub y. F sub y of xy. This is equal to the second component, which is e to the x plus x cosine y. Okay. So if we integrate this, so I'll write everything in here. So we integrate this guy here, okay, with respect to y. We also integrate this guy here, e to the x plus x cosine y with respect to y. So we will have f of xy. We treat x as constant, okay? So if we integrate the right-hand side, we'll just have what? Y, e to the x. And then the integral of cosine y, that's sine y. So we will have here x sine y. And then plus some constant. But we are treating x as constant. So this constant now is a function of g. Is a function of x, I mean. Okay? So this is a function of x. So if this is really conservative, we should be able to get a function in terms of x only for this g of x. Okay? So now, this is our possible potential. That's your f already. But we need to identify this g of x. So the next step, we differentiate with respect to x. So f of x comma y. So again, we are differentiating with respect to x. We have here y e to the x plus x sine y plus g of x. So in here, we'll end up with f sub x comma y, or f sub x of x comma y. On the right-hand side, we are treating y as constant. So for this guy, it's still y e to the x. For this guy, it's just sine y. So plus sine y. And then for this guy here, it's g prime of x. Okay? But then again, this is f sub x. This is your first component here. So which means we will have first component, it's y e to the x plus sine y. For the second component, you have y e to the x plus sine y plus g prime of x. And this gives us what? G prime of x equals 0. And of course, this is just a constant. Okay, it is a function of x. But the function whose derivative is equal to 0 are the constant function. So g of x, this is equal to some constant c. Okay? Which means that thus f is indeed conservative, okay? With potential of the form, so we have f x comma y. So this is equal to y e to the x plus x sine y plus some constant c. So this is our final answer. Okay? Questions?